Welcome to the deep dive. Today we're going deep on a cornerstone of fluid mechanics.
Oh, sounds exciting.
It is actually the Bernoulli equation.
Okay.
We've got excerpts from a textbook chapter actually on elementary fluid dynamics. We're going to break down this fundamental equation
Okay.
and its real-world applications.
Awesome.
So buckle up. This is where it gets really interesting.
You make even fluid dynamics sound exciting. Let's dive in.
Perfect. So how do we even begin to understand this Bernoulli equation? I mean, fluids are constantly moving, changing.
Right.
It feels almost impossible to predict their behavior.
You're right. It's complex, but the Bernoulli equation helps us make sense of it. At its heart, it's really a statement of energy conservation for fluid flow. We get there by applying Newton's second law, but this time to fluid particles instead of solid objects.
That's interesting. I remember Newton's second law from physics class.
Yeah.
But I never thought about applying it to something as fluid and dynamic as, well, a fluid.
It's a clever leap, isn't it? We start by considering the forces acting on a tiny volume of fluid,
Okay.
the fluid particle as it moves. Primarily, these forces are pressure and gravity.
So the pressure pushing on the particle and gravity pulling it down.
Exactly.
It's like a tiny tug-of-war happening at a microscopic level.
A fantastic way to picture it. Now, to simplify things, we initially assume the fluid is inviscid, meaning we're neglecting friction.
So we're picturing this idealized fluid that flows without any resistance. But how realistic is that? I mean, in the real world, things are never that smooth.
You bring up a crucial point. No fluid is truly inviscid.
Right.
But this simplification helps us grasp the core principles. And surprisingly, in many cases, it's a pretty decent approximation.
Okay.
Think about water, for instance. Viscous forces are often much smaller compared to the forces from gravity or pressure differences.
That makes sense, like when a leaf gets swept away by a strong current in a river.
Exactly.
The force of the water pushing it is much stronger than any friction from the water itself.
That's a perfect illustration.
Okay, so we've got our tiny, frictionless fluid particle.
Right.
We're considering pressure and gravity.
Right.
Where do we go from here?
Well,
How do we get to the actual Bernoulli equation?
the next step involves some calculus, but we'll skip the heavy math here.
Okay.
The key is that we apply Newton's second law,
Okay.
both along and perpendicular to the streamline of a fluid particle. What we end up with is an equation describing how the speed of that fluid particle changes along its path due to changes in pressure and elevation.
So it's like mapping out the fluid particle's journey, considering the forces that speed it up or slow it down.
You got it. Now, during this process, we make a few assumptions. In addition to assuming inviscid flow,
Okay.
we also focus on steady flow, meaning the flow pattern doesn't change over time.
Got it.
And we assume the flow is incompressible, meaning the density of the fluid remains constant.
So it's a simplified, idealized scenario, but it sounds like those assumptions lay the groundwork for understanding the equation.
Precisely. And these assumptions are often reasonably accurate for many real-world flows.
Okay, that's reassuring. So after all that work and those assumptions, what does this magical Bernoulli equation actually look like?
It states that the sum of three terms remains constant along a streamline.
All right, let's break down this equation piece by piece. What does each term represent?
Each term represents a form of energy per unit weight of the fluid.
Okay.
Think of it like this. We're talking about energy, but instead of measuring it in joules, we're measuring it in units of length, like feet or meters.
Interesting. So we're talking about the energy of the fluid, but we're expressing it in terms of height.
Exactly. Let's start with P. It represents the static pressure at a point in the fluid. This is the pressure you'd measure if you were moving along with the fluid, hence static.
So it's the pressure at that point as if we were just floating there with the fluid.
Precisely. Next, we have 1/2 rho times V squared. We get the dynamic pressure.
So dynamic pressure has something to do with the fluid's motion.
Exactly. It's the pressure increase you'd see if the fluid suddenly stopped. Imagine a jet of water hitting your hand.
Okay.
That forceful impact is related to dynamic pressure.
Wow. That's a great way to visualize it. So we've got the static pressure, the dynamic pressure.
Right.
And what about the last term? How much potential energy the fluid has because of its height.
Yes.
It's like a ball held up high. It has the potential to fall due to gravity.
You nailed it. We call this the elevation head.
Okay, let me make sure I've got this right.
Okay.
The Bernoulli equation tells us that the sum of the pressure head, the velocity head, and the elevation head stays constant along a streamline. And each of these heads represents a form of energy, but expressed in units of length.
A perfect summary. And this seemingly simple equation has a wide range of applications.
And that's what I'm excited about. So let's get into those applications. What are some real-world examples of how the Bernoulli equation is used?
One of the simplest examples is a free jet, like water flowing from a tank. Imagine punching a hole in a water bottle.
Oh, I've done that plenty of times.
Yeah.
But I never thought about the physics behind it.
It's more fascinating than you might think. By applying the Bernoulli equation, we can predict the velocity of that jet of water. And what's remarkable is that this concept was discovered way back in the 17th century by Evangelista Torricelli.
Wow, that's going way back. Wait a minute. Are you saying that the water shooting out of a hole in my water bottle is moving at the same speed as if I dropped a marble from the water level?
You got it.
That's mind-blowing.
It is. It highlights a beautiful connection between fluid dynamics and simple physics.
And I never would have guessed that those two things were related. So the Bernoulli equation helps us understand free jets. But what about flows that are confined, like in pipes?
Right?
How does the equation work there?
In confined flows, we need to use the Bernoulli equation in conjunction with the continuity equation, which is all about mass conservation. Essentially, the continuity equation tells us that the mass flow rate,
Okay.
the amount of mass flowing per unit time, has to stay constant along a streamline.
So if the pipe gets narrower, the fluid has to speed up to keep the same amount of mass flowing through. Like squeezing a tube of toothpaste, the toothpaste comes out faster because you're making the opening smaller.
A great analogy. This relationship between flow area and velocity, combined with the Bernoulli equation, is what lets us analyze flows in pipes and other confined spaces.
Okay, I'm starting to see how these equations work together. Can you give me a real-world example of how this is used?
Let's consider a pipe reducer, where the diameter of a pipe suddenly decreases.
Okay.
Think of it like when a plumber uses a fitting to connect two pipes of different sizes.
So as the water squeezes into that smaller section of pipe,
Right.
its velocity increases to keep the flow rate constant. And according to Bernoulli, if the velocity goes up, the pressure has to drop.
You're right on track. And that's exactly why we see a pressure drop across a pipe reducer. It's because the water is being forced to speed up.
That's pretty cool. I never realized there was a pressure drop in those situations. It makes sense now, though.
And this principle of pressure drop, due to increased velocity, is the key to how many flow meters work.
Okay.
These are devices that measure how much fluid is flowing through a pipe. You've probably seen them in industrial settings or even in your home's water system.
Flow meters, those devices that tell us how much water we're using.
Exactly. And devices like orifice meters, nozzle meters, and Venturi meters
Okay.
all rely on the Bernoulli equation. They work by creating a deliberate restriction in the pipe,
Oh, interesting.
causing the fluid velocity to increase and the pressure to drop. By measuring the pressure difference across that restriction, we can calculate the flow rate.
It's like intentionally creating a bottleneck in the pipe and then using the pressure difference on either side to figure out how much water is squeezing through.
A fantastic way to put it. The relationship between the pressure difference and flow rate is actually quite straightforward. The flow rate is proportional to the square root of the pressure difference.
That's amazing. So these flow meters for pipes use the Bernoulli equation.
Hmm.
Are there similar devices for measuring flow in open channels like rivers or irrigation canals?
Absolutely. We have things like sluice gates and weirs that are commonly used in open channel flows.
Sluice gates. Those sound intriguing. What exactly are those?
Imagine a gate that can be raised or lowered to control the flow of water in a channel. That's a sluice gate. It acts like a barrier that creates a difference in water levels upstream and downstream.
So by raising or lowering the gate, we can control how much water flows through.
Precisely. And the flow rate through a sluice gate depends on the difference in water depths on either side of the gate. The greater the difference, the higher the flow rate.
It's like the water is being forced through that opening under the gate, and the difference in water levels on either side is what drives the flow.
That's a good way to visualize it. And by applying the Bernoulli equation and the continuity equation, we can come up with a formula that relates the flow rate to the water depths and the width of the gate opening.
So sluice gates give us control over the flow, and they can also be used to measure it.
Right.
What about weirs? How do they work?
A weir is a structure placed across a channel,
Okay.
typically with a notch or opening of a specific shape. As water flows over the weir, the depth of the water above the weir crest relates to the flow rate.
So it's like a mini dam, but instead of completely blocking the flow, it lets the water spill over the top.
Precisely. Weirs are especially handy for measuring flow rates in situations where the water level is relatively constant, like in an irrigation canal.
Okay, so I've got sluice gates and weirs for open channels, and they both rely on the Bernoulli equation and the continuity equation to connect flow rate to water depth. It's incredible how these relatively simple equations have such diverse applications.
It really is. And the Bernoulli equation isn't just some theoretical curiosity.
Right.
It has very real-world implications in everyday life, from designing airplanes to understanding how blood flows in our bodies.
That's amazing. But before we get too carried away, what are some of the caveats and restrictions of the Bernoulli equation? I mean, no equation is perfect, right?
You're absolutely right. The Bernoulli equation is a powerful tool, but we always need to remember it's based on certain assumptions. If those assumptions aren't met, the equation might not accurately predict what we see in the real world.
So what are some of the red flags to watch out for when using the Bernoulli equation?
The first one is that we assumed inviscid flow, meaning we ignored friction. But all fluids have some degree of viscosity,
Right.
and that can lead to energy losses that the Bernoulli equation doesn't take into account.
So if we use the equation without considering friction, we might overestimate the velocity or pressure in a real system.
Exactly. And the impact of friction can be quite significant in situations where the flow is turbulent or where the fluid is moving through a long, narrow pipe.
Okay, friction. That's one to remember. What else might throw off the accuracy of the Bernoulli equation?
We also assumed that the flow is steady. However, in many real-world situations, the flow can be unsteady, meaning it fluctuates or changes direction.
So if the flow is swirling around or pulsing, the Bernoulli equation might not give us an accurate picture.
That's right. An unsteady flow can be tricky to analyze because the velocity and pressure are constantly changing.
Got it. Steady flow, check. What about that last assumption, incompressible flow?
Yes, we assumed the fluid's density remains constant. This is generally a good assumption for liquids,
Okay.
but might not be accurate for gases, especially at high speeds.
But wait, doesn't air get thinner at higher altitudes?
Right.
How does that play into the equation when we're talking about airplanes?
That's a sharp observation. And you're right, it does play a role. At those high speeds and altitudes, the air's density can change significantly, and that could affect the results we get from the Bernoulli equation.
So the density of the fluid is another factor we need to keep in mind. What are some other situations where the Bernoulli equation might fall short? Are there any other phenomena we should be aware of?
There is one more critical limitation to consider: cavitation.
Cavitation. That sounds a bit ominous.
It can be. It's a fascinating but potentially destructive phenomenon that can occur in fluid systems.
Well, now I'm definitely intrigued. Tell me more about this cavitation thing. What exactly is it? So you're about to explain cavitation. What exactly is it?
Cavitation happens when the pressure in a liquid drops below its vapor pressure.
Vapor pressure. That sounds familiar. Isn't that the pressure at which a liquid starts to boil?
That's it. We typically think of boiling as something that happens at high temperatures, right?
Right.
But here's the thing. If the pressure is low enough, a liquid can actually boil even at relatively low temperatures.
So even cold water can start to boil if the pressure drops too low.
It is.
That's counterintuitive.
And that's precisely what happens in cavitation. When the pressure in a liquid falls below its vapor pressure, vapor bubbles begin to form.
Okay, so we've got these vapor bubbles forming, but you said cavitation can be destructive. How do these seemingly harmless bubbles cause damage?
The problem is that these vapor bubbles are unstable. As they drift into regions of higher pressure, they collapse violently.
So it's like those tiny bubbles are imploding.
Exactly. And these implosions release intense shock waves that can erode nearby surfaces. Imagine tiny explosions happening constantly within the fluid. It can really wreak havoc on equipment.
Wow. I wouldn't have guessed that those little bubbles packed such a punch. So how does cavitation actually happen in a real-world fluid system?
One common scenario is a pressure drop caused by an increase in fluid velocity. Remember our friend the Bernoulli equation. As velocity increases, pressure decreases.
So if the fluid is zooming through a narrow section of pipe, for example, the pressure could plummet low enough to trigger cavitation.
Precisely. That's why cavitation is a major concern in systems with high fluid velocities like pumps, turbines, and even ship propellers.
Okay, so if I were a ship captain or a power plant operator, I definitely want to keep an eye out for cavitation. Are there any telltale signs that it's happening? Like any warning signals?
One of the most obvious signs is a distinct hissing or crackling sound coming from the system. This is caused by the formation and collapse of those pesky vapor bubbles.
So it's like the fluid is whispering, hey, there's some cavitation going on here.
You could say that. And if we ignore those whispers and allow cavitation to continue unchecked, it can cause serious damage to equipment over time, leading to costly repairs or even system failures.
That's definitely something we want to avoid. So what can we do to prevent cavitation? Are there ways to design systems that are less susceptible to it?
There are several strategies we can use. One approach is to design fluid systems in a way that minimizes areas of high velocity and low pressure. This might involve using larger pipes or smoother transitions to reduce the chances of those pressure drops that trigger cavitation.
So it's about making the fluid's journey as smooth and gradual as possible. No sudden turns or narrow passages where the pressure might plummet.
You've got the idea. Another tactic is to use materials that are more resistant to cavitation damage. Certain alloys or coatings can better withstand those intense shock waves produced by the collapsing bubbles.
So tougher pipes, basically.
Yeah.
It's like giving the system armor to protect it from those little explosions.
A great analogy. And in some cases, it might be necessary to increase the system's overall pressure to prevent it from falling below the vapor pressure. This could involve using a more powerful pump or adjusting the system's operating parameters.
So careful design, material selection, and pressure management are our allies in the fight against cavitation.
Exactly. And it's essential to be aware of the potential for cavitation in any fluid system where we might have those risky combinations of high velocities and low pressures.
Well, I think we've covered a lot of ground here with the Bernoulli equation.
Yeah,
Its derivation, its applications, and even its limitations.
we have.
It's fascinating how this one equation can explain so many different phenomena.
It really is a versatile tool. But there's another fascinating aspect of the Bernoulli equation I'd like to explore. It's different interpretations. It's not just about numbers and symbols. We can gain deeper conceptual understandings from it as well.
That's what I love about the deep dive. We go beyond the formulas and explore the bigger picture. So let's talk about those different interpretations. What are some of the ways we can think about the Bernoulli equation conceptually?
One way is to view it as a statement of energy conservation for fluid flow. Remember those different heads we discussed? Pressure head, velocity head, and elevation head.
Right.
Those represent the different forms of energy present in the fluid.
And we said that the Bernoulli equation tells us that the sum of those heads stays constant along a streamline.
Exactly. Now imagine a tiny fluid particle traveling along its path. As it moves, its energy can be transformed between those different forms. It's like the particle has a budget of energy that it can allocate to moving faster, climbing higher, or increasing its pressure.
So it's like a constant balancing act. If the particle speeds up and gains kinetic energy, it might have to sacrifice some of its potential energy by decreasing its elevation, or it might lose some pressure energy.
That's a perfect way to put it. And the Bernoulli equation tells us that the total energy budget always stays balanced along the streamline, assuming those ideal conditions of inviscid, steady, and incompressible flow.
It's like a fluid version of the law of conservation of energy. But can we also interpret the Bernoulli equation in terms of pressure?
Absolutely. We can think of it as a statement of pressure balance. The Bernoulli equation can be written in a form that highlights the different types of pressure acting on that tiny fluid particle as it journeys along the streamline.
Okay, let's break that down. What types of pressure are we talking about here?
Well, we have our familiar friend, the static pressure, the pressure at a specific point in the flow. Then we have the dynamic pressure, the pressure associated with the fluid's motion. And finally, we have the hydrostatic pressure, which is the pressure due to the weight of the fluid above a certain point.
Hydrostatic pressure. That's the one we learned about when we were talking about fluids at rest, right?
That's the one.
Like the pressure at the bottom of a swimming pool.
And it's interesting to note that even though the fluid is now in motion, hydrostatic pressure still plays a role.
So how does the Bernoulli equation connect all these different types of pressure?
The Bernoulli equation tells us that the sum of these three pressures, static, dynamic, and hydrostatic, remains constant along a streamline as long as we stick to those ideal flow conditions.
It's another conservation statement, but this time it's about pressure. It's as if the total pressure acting on that little fluid particle has to stay balanced as it moves along its path.
Precisely. And this pressure balance perspective can be really helpful in understanding how fluids behave in different situations.
So we can think about the fluid's energy budget or its pressure budget, and the Bernoulli equation helps us see how those budgets stay balanced throughout the fluid's journey.
Exactly.
Yeah.
And these different interpretations can be valuable depending on the specific problem we're trying to solve.
It's like we have multiple lenses through which we can view and understand the Bernoulli equation?
Exactly.
This makes the whole concept so much richer and more intuitive.
I agree. And that deeper understanding helps us apply the equation to a broader range of real-world applications.
Speaking of applications, I'm eager to dive into some more practical examples. We touched on airplanes earlier, but how does the Bernoulli equation actually help us understand the magic of flight?
Let's take a closer look at the shape of an airplane wing. It's carefully designed to create a difference in airspeed between the top and bottom surfaces. The air flowing over the curved top surface has to travel a longer distance than the air flowing underneath.
So the air on top has to move faster to keep up.
You got it. And according to the Bernoulli equation, higher airspeed means lower pressure.
So the air pressure on top of the wing is lower than the air pressure underneath. That's how it works.
Precisely. And this pressure difference generates an upward force, we call it lift, which counteracts the weight of the airplane and keeps it aloft.
So it's all about manipulating the airspeed, using that clever wing shape. And the Bernoulli equation helps us connect that airspeed difference to a pressure difference, which ultimately creates lift.
That's a fantastic summary. It's important to remember that while the Bernoulli equation is crucial in understanding lift, it's not the whole story.
No.
Factors like the wing's angle of attack and the viscosity of the air also play a role.
Okay, so the Bernoulli equation gives us a good starting point, but there's more to the picture.
Mm-hmm.
What other real-world applications can we explore with this equation? I'm curious to see how it pops up in unexpected places.
Well, believe it or not, the Bernoulli equation is also key to understanding things like perfume atomizers and paint sprayers.
Perfume atomizers and paint sprayers. Those seem so different from airplane wings. How can the same equation apply to all of them?
The fundamental principle is the same, creating a pressure difference by manipulating the fluid velocity. Let's take a perfume atomizer as an example. When you squeeze that little bulb, you force air to flow rapidly over the top of a small tube dipped into the perfume.
So we're creating a jet of fast-moving air. But how does that help get the perfume out?
That fast-moving air creates a low-pressure area above the tube. And this low pressure is what draws the perfume up the tube and out into that fine mist we all know and love.
So the perfume is basically being sucked up by the low-pressure area created by the fast-moving air. That's so clever.
Exactly. And the same principle is at work in paint sprayers, where compressed air is used to create a high-velocity jet of air that pulls paint up into the sprayer and transforms it into a fine spray.
It's amazing how this one equation can connect such diverse applications. It's like a hidden thread weaving through all sorts of everyday devices and phenomena.
It really is. It's a beautiful example of the power of physics to connect seemingly unrelated things.
Okay, we've talked about airplanes, perfume atomizers, and paint sprayers. Wow, the list goes on and on. It seems like the Bernoulli equation is everywhere if we know where to look.
You're absolutely right. It's a fundamental principle governing the behavior of fluids, and its applications are vast and varied.
Okay, let's pick one more example to really solidify our understanding. What about the flow of water through a fire hose? I imagine the Bernoulli equation must play a role there, given the high pressures and velocities involved.
That's a great example. Picture a fire hose hooked up to a fire hydrant. The water inside the hydrant is under high pressure, but it's not moving very fast.
So we have high pressure, but low velocity to start with.
Exactly. As the water starts flowing through the hose's diameter decreases, causing the water velocity to increase.
And according to Bernoulli, if the velocity increases, the pressure has to decrease. So the water is speeding up, but the pressure is dropping as it moves through the hose.
You've got it. And then the water reaches the nozzle at the end of the hose. The nozzle further constricts the flow passage, which causes the water velocity to shoot up even higher, leading to a dramatic pressure drop right at the nozzle exit.
So that's why the water blasts out of the nozzle with such force.
Yes.
It's all about that pressure difference between the hydrant and the nozzle.
Precisely. That pressure difference created by the changes in velocity is what drives the flow of water through the entire system.
It's like a carefully choreographed dance between pressure and velocity, all orchestrated by the Bernoulli equation. It's amazing how something as seemingly simple as squeezing a garden hose or watching water flow from a tank can be explained by this one elegant equation. It's truly the foundation for understanding how fluids behave in the world around us.
It is, and we've only just scratched the surface of the fascinating world of fluid dynamics.
Well, that brings us to the end of our deep dive into the Bernoulli equation. It's been an incredible journey exploring the Bernoulli equation. I feel like I've gained a whole new perspective on how fluids behave. But before we wrap up, you mentioned something earlier about visualizing the Bernoulli equation.
Yeah.
Something about an energy line and a hydraulic grade line.
Yes.
Those sound intriguing.
They are. These graphical representations can help us visualize how energy and pressure are distributed within a fluid system.
Okay.
It's like having a map that shows us the energy landscape of the flow.
A map of the energy landscape. I love that.
Yeah.
So let's start with the energy line. What exactly is that?
The energy line, often shortened to EL, represents the total head available to the fluid at any given point along a streamline.
Total head. That's the sum of the pressure head, velocity head, and elevation head, right?
Yeah.
Like the fluid's total energy budget at that specific location.
Exactly. The EL tells us how much energy the fluid has, taking into account its pressure, speed, and height.
Okay.
It's a powerful way to visualize the energy dynamics of the flow.
So how do we actually determine this energy line? Do we need some fancy equipment to measure it?
One way to visualize the EL is to use a series of Pateau tubes placed along the streamline.
Pateau tubes. Those are the devices that measure stagnation pressure, right? Like
Yeah.
the pressure that would build up if the fluid were suddenly brought to a stop at that point.
Precisely. And remember that stagnation pressure represents the total pressure,
Yeah.
which includes both the static pressure and the dynamic pressure.
Right, so a Pateau tube gives us a measure of the fluid's total energy at that point.
Exactly. If we have a series of these Pateau tubes placed along the streamline, we can measure the stagnation pressure at each point.
Okay.
We can then plot those pressure values on a graph, and the line connecting those points gives us the energy line.
So it's like we're creating a topographical map of the energy levels within the flow. Are there any patterns or characteristics we typically see in the energy line?
That's a great way to think about it. And under those ideal conditions we keep talking about, steady, inviscid, and incompressible flow, the energy line should be horizontal.
A horizontal line. Why is that?
Because according to the Bernoulli equation, the total head remains constant along a streamline under those conditions. So even if the individual heads change, for example, an increase in velocity head might be offset by a decrease in pressure head, the total head or the overall energy level stays the same.
That makes perfect sense. The horizontal energy line is a visual representation of the conservation of energy within the flow. Now, what about this hydraulic grade line you mentioned?
Okay.
How is it different from the energy line?
The hydraulic grade line, or HGL, focuses on the sum of the pressure head and elevation head at any point along the streamline.
So it's like the EL, but it doesn't include the velocity head.
Exactly.
It's more about the potential energy of the fluid due to pressure and elevation.
Exactly. To visualize the HGL, we can use piezometer tubes placed along the streamline.
Piezometer tubes, those are the simpler ones that just measure static pressure, right?
You got it.
No need to bring the fluid to a stop, like with the Pateau tubes.
So the HGL essentially plots the static pressure along the streamline, adjusted for changes in elevation.
And unlike the EL, the HGL doesn't have to be a straight horizontal line, right?
That's right. The HGL can slope upward or downward depending on changes in the fluid's velocity.
Why is that? How does the velocity influence the slope of the HGL?
Remember our friend, the Bernoulli equation?
Of course.
It tells us that as velocity increases, pressure decreases.
Right.
So if the fluid speeds up, the pressure head drops, causing the HGL to slope downward. Conversely, if the fluid slows down, the pressure head increases and the HGL slopes upward.
So we can actually deduce information about the fluid's changing speed just by looking at the slope of the HGL. That's pretty neat.
It is. And here's another interesting tidbit. The distance between the EL and the HGL at any given point actually represents the velocity head at that point.
So we can literally see the velocity head represented visually as the gap between those two lines. That's a powerful visualization tool.
It is. And the EL and HGL are not just theoretical concepts. They have practical implications in the real world, particularly in designing and analyzing fluid systems.
Now we're talking. Can you give me an example of how engineers might use these lines in a real-world project?
Let's imagine engineers designing a pipeline to transport water from a reservoir to a town. They would use the EL and HGL to make sure the pressure in the pipeline stays within safe limits, and to ensure that the water arrives at its destination with enough pressure to be useful.
So it's like a visual checklist to make sure the water pressure isn't too high or too low at any point along the pipeline.
That's a good way to think about it. The HGL can help identify potential problem areas where the pressure might be too low,
Right.
which could lead to issues like pipe collapse or even that cavitation we talked about earlier.
And the EL would help ensure that the water has enough energy to make it all the way to the town, considering any changes in elevation along the way.
Exactly. The EL would take into account those changes in elevation and make sure the water has enough potential energy to overcome those uphill climbs, so to speak.
It's incredible how these lines provide a visual roadmap for understanding and managing the fluid flow in such a complex system. It's like they're giving us a peek into the inner workings of the flow.
They do, and they highlight the importance of considering both energy and pressure when designing and analyzing any fluid system.
Well, I think we've truly explored the depths of the Bernoulli equation and its implications. We've covered everything from its theoretical foundations to its practical applications, and even delved into some fascinating ways to visualize its principles.
We have. It's been a rewarding journey through the world of fluid dynamics.
It has. And hopefully our listeners have come away with a newfound appreciation for this elegant equation and its profound influence on our everyday lives.
I hope so too. It's a testament to the power of physics and mathematics to help us understand the world around us.
Absolutely. And remember, this is just the beginning. There's a whole universe of fluid dynamics waiting to be explored. So, until next time, keep asking questions, keep exploring, and keep diving deep.
Well said. And remember, the world of fluids is full of surprises and fascinating phenomena. You just need the right tools and perspectives to unlock its secrets.